Okay, welcome back. So we are at Unit 5, Module 7. Okay, so again, once upon a time we have talked about what is a we have the autocorrelation function and the power spectral density, right? Or the power density spectrum and the autocorrelation function. And we know that both of these are related to each other by the Fourier transform, right? That means the Fourier transform of the time averages of the autocorrelation function is equal to the power density spectrum, and vice versa. The inverse Fourier transform of the power density spectrum is equal to the time averages of the autocorrelation function. And we have studied that both of these form transform pairs, Fourier transform pairs. Now again, today we are going to study another such relation between the cross power density spectrum and the cross correlation function. Both of these functions, one is the function in the time domain, or it is a function of time. The other being a function of frequency. Both of these are again Fourier transform pairs. So we will derive such a relation in the following course. Now we know the power density the cross power density spectrum is a function of omega, and it is denoted by capital S of omega. Similarly, the cross correlation function is denoted by Rxy of one random variable at the time from the capital X at time point t, and another random variable from capital Y at time point t plus tau. Now we are trying to obtain this here, the cross correlation of two random variables from each of these processes. One random variable is x of t, the other random variable is y of t plus tau. Now we would like to study by using this function, we would like to study what is the time dependency of these random variables which are at time t and t plus 2, which are at a distance of tau from each other. Okay, now following is the statement of the proof of the problem. Prove that for real processes, unless we are told, we assume that the capital X and capital Y are always real processes. That means the sample functions of each of these processes take only real values. They do not take complex number values. Okay, that is the problem. Now, so we want to find out this. Prove that what? We want to prove that the PSD and the time averages of the autocorrelation function, they form a Fourier transform pair. So first we will take this following. So this proof is exactly or almost it is identical to the proof that we have gone for the other Fourier transform pair. Okay, for the power density spectrum of a random process and the autocorrelation function, the proof here is also similar to that. Only thing is we put an additional y here for both of these two functions, capital S of xy and rxy, except that there is no difference between the proofs. Okay, you please identify that. So I will stress here what are the important steps that are used to prove this theorem. First of all, we want to prove that these are Fourier transform pair. So we take first of all the inverse Fourier transform of the cross PSD, which is on the left hand side. Now this is the normalizing constant 1 by 2 pi. It is a normalized constant of the inverse Fourier transform, right? And that is given by this integral minus infinity to plus infinity sxy of omega times the kernel function, which is a complex sinusoid function e power j omega t. Okay, e power plus j omega t and d omega. So by taking the inverse Fourier transform of this function, we want to prove that this is equal to on what is on the right hand side. Okay, we want to prove this result, that the inverse Fourier transform of the cross PSD is equal to the time averages, the average of the cross correlation over time. Okay, now so we will consider the proof. The first step, we will take the cross PSD, and what is that? Sorry, I'm sorry. So this is the okay. Anyway, please continue this. So here, this is the we take the inverse. This is the inverse of the cross PSD. We get the time averages of the cross correlation function. Similarly, this is the forward transform. That is, the Fourier transform is equal to the integral minus infinity to infinity of the time averages function times the kernel of the forward Fourier transform, which is e power minus j omega t dt. Okay, so now dt. Now we want to prove this result, that this is true. So what we do is, it is just sufficient if we prove either one of these two. That is, if we prove either one of these two. Okay, now the time averages of a quantity q of t is defined as capital A of q of t is equal to the limiting value of s t tend to infinity of the time average, that is 1 by 2t integral minus t to t of the function q of t. Now we know that this is the result. We start by taking the expression of the cross power density spectrum sxy of omega, that is equal to the limiting value of t tends to infinity of the expectation of this expression here, that is 1 by 2t times x conjugate and y of omega. Now here, what are capital X and capital Y? These are not these are not the random process. This is a slight difference, because you have to look, this is a function of omega, so it is some kind of a Fourier spectrum. So this first one, that is capital X of omega, is a Fourier spectrum of the sample x of t. Similarly, y of omega, capital Y of omega, it is a Fourier transform of, or the Fourier spectrum of the signal y of t. Okay, you have to note the difference here. X and y, capital Y, they do not denote that they are processes. Only you have to study this. You have to join with this omega, and because this is a function of omega, then it is a Fourier spectrum, not a process. Okay. Note that point. Now, star is a complex conjugate of that Fourier transform or the complex number at that particular omega. Okay. Now, now we have to substitute what is our Fourier transform in each case. So the first xt of omega conjugate is now substituted with this one. That means it is a Fourier transform of the conjugate and taking over the conjugate. Now what would happen to the e power minus j omega t1? It becomes the conjugate. Simply x of t1 is a real number, so we have to leave it like that. But this is a complex number, so this will be conjugated. Similarly, the second Fourier transform of y of t is given by this expression. It is the Fourier transform of y of t within the interval minus t to t. So hence the limits are from minus t to t and y of t2, where t2 is a dummy variable, and e power minus j omega t2. Here in this case, I have chosen different dummy variables for each of these integration. It is quite simple. It is rather more informative to take two different dummy variables than rather put t and t here. Simply, this is very general case. Normally what would you do? We have to put this as a separate Fourier transform and this is a separate Fourier transform, right? So each one will be on a different time scale times, hence a different variable. Okay. Now what will happen to this expression? Now we can write x of t1 and y of t2 as together, and we can join this complex exponential as e power minus j omega t2 minus t1. Now this expectation is on the outside. Now we can take this inside the integrals without changing the value of this expression. Now here in this integrand, what are the random variables? The random variables are only x and y, whereas other expressions, that is the complex exponential, is a constant with respect to, it is a normal variable, it is not a random variable. Therefore this expectation only applies to these two random variables. Now by taking it inside, we get expectation of the product of these two random variables. Okay, and this is left outside as a constant. Okay, got the point? Now we can write down, we note this one. What is this expression here? That is the expected value of the product of two random variables at different time points. Simply it is given by the cross correlation. It is given by the cross correlation function between the time points t1 and t2. Hence we have to write this as r xy of t1 comma t2. Got it? Let's move on. Now by substituting that, I get this following expression. Now I will, so in order to further simplify this expression, I will make a change of variables. That means I will substitute this following change of variables, that is t1 is equal to t. Therefore dt1, that the differential of t1 will be equal to dt. Okay. Similarly, the t2 is substituted for t1 plus tau, or t2 minus t1 is equal to tau. Now this t1 is equal to t, so we have to replace that. Now in this implies that here t2 is a variable. Similarly tau is a variable for a specific t1. Therefore, the t1 is a constant with respect to this variable. Therefore, dt2 or the differential of t2 is equal to the differential of tau. Now, by substituting this result, we have the following, that is, the e power minus j omega t2 minus t1 is replaced with tau, and dt1 is replaced with dt, and similarly the d22 is replaced with d tau. Now the autocorrelation, the cross correlation function becomes this one by substituting t1 and t2. Okay, now what happens to the integrals? Now for the t, as t goes from minus t to t, as t goes from minus t to t, the value of dt2, or sorry, the value of tau takes values from minus t to t minus t. Okay, in fact we can substitute this one as t is equal to minus t. Let's say as t is equal to minus t, what is the value taken by tau? It is minus t minus t. Okay, as t is equal to small t is equal to capital T, we can substitute that into this expression to find out what is the value of tau. Tau takes value whatever this value t, capital T minus t. Okay. Now I can cloud by looking at that expression here. We can see that now I can take this limiting integral, the limit value, or into this, inside this integral, into this integral. What will happen? This will be the limiting value of the average of the autocorrelation function, right? So we get this by clubbing this integral, we get the following. So whatever this one is, the limiting value of t tends to infinity of the average of the autocorrelation function between the limits minus t to t. Now this expression, we know it as the time averages function, the time averages of the cross correlation function. Now I can substitute that for capital A of rxy of t comma t plus tau. Hence we have proved the very first fundamental result, that the cross PSD is equal to the Fourier transform of the time averages function. Okay. Now if the Fourier forward transform exists, that is, if this is true, then the inverse is automatically exist. So we don't need to prove the inverse relationship. We can automatically say that since the Fourier transform of the time averages is equal to the cross PSD, the inverse also is true. Hence these two functions, that is the time averages of the cross correlation and the cross PSD, they form Fourier transform pairs. Thank you very much.